Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the topic cleaner route for energy production from coal. In the last class we have discussed on the conventional route for energy production from coal, and we have seen that combustion based thermal power plant is the most conventional route for energy production from coal. And in this process coal is burned in a furnace and then flue gas, which is having high temperature, is passed into the boiler for the production of steam, and then the steam is used in turbine for electricity production. Now, here we will discuss what are the possibilities to make more cleaner energy than the conventional one, because in the conventional process we have seen that the emissions are higher, the SOx, NOx and CO2 emission are higher. So, if we want to reduce the emissions, what can be the possible routes, that part we will discuss in this class. As you know, prevention and control, these are two important philosophy for the management of something or to achieve our target quality. So, in this case we can try to prevent the emission level, or we can take measures to control the concentration of the pollutants present in the flue gas by its cleanup. So, one is our prevention, that means that is related with feedstock, that is the coal which we are using, we may clean it, or during the process of combustion when the flue gas is forming, at that time we can take some modification in the process, so that we can get less emission through this process. Or we can also use some alternate techniques in place of combustion. So, that way we can control the emission level. Now, these are the contents of our discussion, that pre-treatment of coal, that means here we are interested to clean the coal before its application, and modification in process, we can use the different types of reactor, improved reactor, and then the boiler device that can be of supercritical type and flue gas cleanup, and we can use some advanced techniques like oxy-fuel combustion, chemical looping combustion, and then gasification, direct liquefaction and underground coal gasification. Now, we will see this is the conventional flow sheet. Say here coal is burnt in the furnace and then flue gas is going, and here we are recovering the heat, then it is going for cleanup section and coal is put here. So, this is the conventional process. Now, what we can do? We can clean the coal in higher extent, we can use more efficient furnace, or we can use more efficient heat recovery system, or we can use more superior quality of gas cleanup processes, or some advanced techniques. As shown here, this line are related with oxy-fuel combustion. Oxy-fuel combustion, another method which is the replacement of the combustion process. So, here nitrogen is separated at first from the air, and so only oxygen we can use. So, if we use more oxygen, the flue gas will be having more carbon dioxide, it will not be having nitrogen. So, once it is not having nitrogen, its capture will be very easy. So, carbon dioxide capture we can get here, and the whole process will be more cleaner. So, these are the scopes which we have to improve the cleanliness of the process or to reduce the emission level. So, we will discuss all those things. At first we will say how the coal is cleaned. As on today, in the conventional process also coal cleaning is performed to remove the ash and to sulphur. So, we have to take more action if we can reduce the pollutants level like say sulphur, ash content, nitrogen content in the coal. And what are those methods is used, we will be discussing now. If we consider the sulphur, then sulphur is present in coal in terms of inorganic and organic form. In the inorganic form basically it is pyrites, FeS2, and some others are also there, that is ZnS, PbS and FeS2. This is your marcasite and another is your pyrite. So, pyrite and marcasite, two ore, these are two minerals are having same formula, but they are different in their crystal structure. So, these are the source of sulphur. So, we can remove this sulphur from the sources by different methods. One is physical, then chemical and biological. How we can remove? In the physical method, we can use the help of jigging, we can use the tabling, we can use the dense media processing, hydrocycloning and air classification. So, in the jigging we take the advantage of the difference in the initial acceleration when the different particles start to fall from a certain place from its rest position, then initially they possesses different velocity. So, that will be utilized to remove the different particles with different density and size etc. That is the jigging operation. And dense media processing, in this case we use certain slurry that is having certain specific gravity. Now, coal is heterogeneous sample and it will be having ash, carbon and etc. So, number of particles if it has, then that will be having different density, say rho 1, say different densities are there for coal, say rho 1, rho 2, rho 3, rho 4 etc. So, different particles are different density. If we use one slurry solution, that is the specific gravity is equal to say rho 3. So, in that case the lighter than rho 3 that will float and heavier than rho 3 will fall. So, this is the way we can get, if rho 4 is higher than this rho 3, then rho 4 will come at the bottom and this will be at the top. So, gradually if we take another solution which is having lesser density, so more lighter particles will also come up. So, that way we can clean the coal from the impurities like say ash contents, mineral contents, basically mineral contents which are having higher specific gravity than the coal particle. So, now the chemical methods, this method, the physical method are suitable to remove the minerals, but which is the sulphur which is available in organic form, those are not very easy to separate by this method. So, chemical methods are used in this case. So, some examples are oxydesulfurization process. In this case oxygen in dissolved form in some solution, aqueous solution at elevated temperature and pressure are used, so that the sulphur of the pyrites is oxidized, or organic sulphur can also be oxidized to some extent. And then hydrodesulfurization, where if we supply hydrogen and high temperature control, if we have good control on it, so we can get some conversion of the sulphides to the sulphur dioxide. So, next is caustic treatment. So, SOx, as you know, it is acidic in nature. So, if we use some alkali solution, caustic solution in controlled amount, so some sulphur can also be removed. And then biological methods, some microbes are used for the degradation of the sulphur compound. Some example are some thermophilic and mesophilic or mesophilic bacteria. Now, we are coming to the changes which we can have during the process. One is fluidized bed reactor. If fluidized bed reactor is used, then we can get more reaction, possibilities of more reactions. How? Because you see here it is a fixed bed and these are the fluidized bed. So, in fixed bed the particles are very closed, I mean fluidized bed the particles are not very close, it is separated. So, coal combustion is a solid and gas phase reaction. So, when the solid particles will be surrounded by more gas molecules, so there will be good chance of the reaction. So, that is why we get more chance of reactions in case of fluidized bed reactor, and in this case the particle size are also less. So, once the particle size is small, then one way we can reduce the loss of the fines of the coal particles, fine coal particles, and second way we can get more interaction of the solid particles with the gas molecules and more rate of reaction. Apart from this fluidized bed reactor can also gives us some other advantage, like say we can add limestone here with the feedstocks. So, feedstocks and limestone is coming here. So, all our solid particles are fluidized and then in situ SOx capture is possible, in situ SOx capture. So, the limestone will react with the SO2 and it will be settled here. So, that is one additional advantage, and if the fine particles are coming here and it is also getting some recycling possibilities. So, more conversions of the carbon we will get here in this fluidized bed reactor. But if we use fluidized bed reactor, then we need smaller particles. So, during crashing we have to use more energy. So, on economic aspect this process may have some less efficiency or it may cost more than the conventional one. Now, fluidized bed size we have in market, that is up to 320 megawatt power plant is possible by this technology. And now we will coming to boiler part. Conventionally subcritical boiler is used at 171 atmosphere and 540 degree centigrade. So, in this case we get 35% net energy efficiency and heat rate is 9751 BTU per kilowatt hour. Now, if we use supercritical, then the operation will be 250 atmosphere and 565 degree centigrade, and here 37% efficiency we are getting. If we use advanced supercritical, then 336 atmosphere and 600 degree centigrade we can get 42% efficiency. If we use ultra supercritical 393 atmosphere at 760 degree centigrade, then we can get 44% energy efficiency. But we see heat rate is decreasing. So, if we it is very clear to us we can improve the efficiency of the process if we replace the subcritical boiler to advanced or ultra supercritical boiler. In this case we can improve the emission level, like the in case of subcritical CO2 926 and at supercritical it is 835 gram per kilowatt hour emission in case of carbon dioxide. For NOx are also here. So, it is very clear that for all the cases we are getting some reductions in supercritical boiling condition. Now, we will come to flue gas cleanup. So, what we can do with the flue gas cleanup? Conventional methods also have some cleanup, but we have to apply more advanced technique for the more efficient removal of the pollutants from the flue gas. One example is say duct injection versus FGD, flue gas desulfurization. So, what happens in case of duct injection? We also use some material, that is solvent is used in duct. Dry solvent is injected in the duct and then it is humidified by the water downstream of the injection, and upstream of the preheater from the particle collection equipment. So, this is the conventional method, but replacing this, if we can use flue gas desulfurization where spray takes place, so scrubbers are used, in that case the efficiency improves for the removal of SOx from the flue gas. Now, regenerative and non-regenerative reagents, we can use the reagents which are regenerative in nature, so that it will help the economy of the process. Wet and dry methods are there. So, wet method flue gas cleanup and dry method is also developed in recent years. So, if we want to use the wet process, then we have to reduce the temperature of the flue gas, and in dry process it can remove the pollutants at high temperature also. That is why there will be some variation in the economy also. Then improved reagent reactivity, the reagent reactivity can be more, if we can select a suitable reagent, the reactivity will be more. So, less reactant requirement will be there, and improved mixing design to lower calcium is to sulfur ratios. So, just fluidized bed reactor, if we can change the design to circulatory fluidized bed reactor, so calcium is to sulfur ratio can be reduced, and larger reactor vessels also helps to get more removal of pollutants, and design removals steadily improving up to 98%. So, one example is given here, and average flue gas desulfurization emission rate is 0.34 pounds sulfur dioxide per MMBTU. So, this is one these are some examples where we have some possibility to improve the efficiency of the cleanup system. Now, this is one example of flue gas desulfurization process taken from this reference. So, here we see flue gas is coming. So, we have limestone slurry, so it is pumped and sprayed here. So, we are getting clean flue gas, and then this slurry part of it is taken back for thickening, and then from this we can get gypsum, and the supernatant from this thickener it is again recycled back to this to reduce the water use. Then after SOx removal, the particulates removal is also important. So, particulates are removed, different types of devices are used to remove particulates, and in case of coal based power plant, mercury may exist as particulate form. So, that removal is also very important, and mercury can be available in oxidized form, in elemental form, and in particulate form, and these different forms of mercury have different solubility. This is water soluble oxidized mercury, and elemental non water soluble. So, the techniques to remove this mercury will also be different. So, people tried to develop effective systems for the removal of complete mercury from the flue gas, and some examples are given here, some configurations. Now, an ESP, the hot side ESP, cold side ESP, fabric filter, and cold side ESP plus spray drying, cold side ESP plus wet flue gas desulfurization, fabric filter plus spray drying, fabric filter plus wet flue gas desulfurization, and ESP plus WFG plus SCR. SCR is selective catalytic reduction. So, these methods have been used for different types of samples, and these are the removal level. Now, we will be discussing on the use of advanced techniques in place of conventional combustion method. So, one example is oxy-fuel combustion. In oxy-fuel combustions, as the term says, we will be using oxygen in place of air. So, nitrogen will be separated from the air first, then oxygen will be used. So, nitrogen is separated from the air and oxygen is used. So, this nitrogen may not be completely removed. So, it is used for the combustion process, and then the flue gas is formed. So, fuel is added here, then flue gas forms, it is going to condenser for heat recovery. So, then the flue gas is again recycled back. So, by this recycling partially we are able to enrich the carbon dioxide concentration in this case. So, more than 90% carbon dioxide we can achieve here. So, it is very easy to sequester. So, that is why this process is very attractive, but research is going on, the commercial plants are yet to come. And then another method is chemical looping combustion. So, in this case some metal are oxidized in one reactor, and in other reactor metal oxidized reacts with the feedstocks, carbonaceous feedstocks, to convert it into CO2 and H2O, and metal oxide is reduced to metal again. So, if we can use two reactors in a cycle, then that can meet our requirement for the production of energy from the carbonaceous materials in one reactor, and other its regenerations of the metal to metal oxide. So, this is one reduction and another is oxidations. So, in this oxidation air is used and metal is converted to metal oxide, and in reduction metal oxide is used is reduced to metal and fuel is converted to CO2 and H2O. So, this is the chemical looping system. So, it is very clear to us in this case when the reaction is taking place we do not need any air. So, nitrogen is not required and only metal oxides are helping for the conversion. So, in that way that will be more cleaner. So, what happens? The metal is oxidized. One example, at 700 to 900 degree centigrade. So, 2 MEO, say Me is the metal and then MEO is the metal oxide, and then metal oxide reacts with carbon, gives CO2 and metal, it reacts with hydrogen, gives metal and H2O. These are the basic reactions. So, we can represent the phenomena in this figure, that this is our fuel. So, this is our metal oxide. So, it will give us H2O plus CO2, and this metal is coming here air. So, it is giving us oxidation and we are getting metal oxide. So, this metal to metal formation, this is exothermic process, overall process is exothermic, and here it is endothermic process. So, these two types of processes are going in the cycle. So, we can get some efficiency of this cycle, and that can be presented by this, that is the Q hot, the amount of heat which is released here, and Q cold, overall energy used in this process, and Q, this is released heat and this is work done during this. So, this is the energy balance, and we can get this relationship, that Q hot is equal to Q cold plus QO plus W. What is this QO? QO is equal to T into del S O. So, there may be some entropy change. So, that is equal to T into del S O is equal to QO. So, this is the chemical looping combustion, and different types of metals and metal oxides are used like copper, iron. When copper is used, this reaction takes place in your oxidizer, that is CO plus O2 CuO, and CuOH2 Cu plus H2 in the fuel reactor, and Cu plus C to Cu plus Cu2 in the fuel reactor. Similarly, for Fe2O4, these are the reactions which takes place in fuel reactor, and this is in the air reactor. So, this chemical looping system is not yet commercialized in a bigger scale, but demonstration has taken place, and total we see 34 pilots of 0.3 to 3 megawatt has run in more than 9,000 hours, and this is the technology which demonstrated in 2003 and later with solid fuels in 2006. Initially it was demonstrated with gas fuels, and 2006 it was demonstrated with solid fuels. And from this data on the demonstration plant, it is very clear that this can be used in commercial scale for the conversion of coal. Now, this slide gives us some example of chemical looping applications in thermal power plant. So, this is in Spain, Germany, Taiwan, US, and this is also US. So, these are the capacities and these are the features. So, it is clear this one we are having calcium based looping system, here we are having limestone based chemical looping system, and this ITRI Taiwan is also using limestone sorbents and with spent CaO, and Alston US they are using CaCaSO4 system, and Ohio State University is using iron oxide based high pressure syngas chemical looping. So, that is for gasification applications. Now, we will see one problem on this. So, calculate the amount of work done in the burning of carbon in a nickel based chemical looping combustion when the change in entropy is 356 joule per K and working temperature is 300 K. So, this is our cyclic process, it is given, we have to calculate the work done, these values we have to calculate. So, now if we have nickel based chemical looping. So, what will be the reactions? What will be the reactions here? What will be the reactions here? That we will consider first. So, here nickel will be oxidized to NiO, the del H is equal to minus 396 K joule kilojoule, and in this carbon will be converted to NiOs. So, then CO2 plus 2A9 is. So, this reactions is 136 kilojoule. Then how we will get Q hot, that is equal to Q cold plus QO plus W as you have discussed. So, Q hot is equal to del H exothermic, that is 396 kilojoule, and Q cold del H endothermic 136 kilojoule, and what is QO? T into del S value is given, T value is given. So, you can calculate the QO T del S, that is equal to this one. So, this joule we are getting. So, we have the relationship, that is Q hot is equal to Q cold plus QO plus W, and by rearranging W is equal to this much. So, now we are able to find out the work done during this process. Next is gasification. Another replacement of combustion is gasification. In combustions we use excess amount of oxygen, in gasification we use controlled amount of oxygen. So, R, that is equal to oxygen by coal ratio, mass by mass ratio. For combustion it is greater than 2.5, and for gasification it is 0.68 to 2.5, and another is pyrolysis, there is no oxygen, in that case we can get R equal to 0.68. So, if we use this gasification method, then what we will get? We will be getting CO and H2, but in case of combustion we are getting H2CO, which is also available in gasification, plus oxygen. So, CO and H2 which we are getting here, so CO2 concentration will be less. So, carbon dioxide production in gasification plant will be less, and we are having CO plus H2 rich gas that can be used for the production of electricity as well as for the production of different types of chemicals. So, we will be having an opportunity to capture carbon dioxide in situ in between, and also to make the syngas in more economical way. So, I will discuss this in next classes in more detail. Now, direct liquefaction, another replacement of oxidation can be direct liquefaction. How it is? Because you see, in coal we have seen in our introductory module that it contains very complex structure containing number of aromatic rings. So, if we can break this aromatic ring and can make some hydrogen addition, so we can get number of organic compounds with aromatic rings, and that is available in conventional liquid fuels. So, direct coal liquefaction can be possible, may be possible if we use higher pressure and hydrogen and required temperature. So, this is done and efforts are going on to get more scale up version of DCL. Already one plant has been commercialized in China, and I have discussed this in detail. Next is underground coal gasification. Another technology possibilities is underground coal gasification. In this case, gasification will take place, but that will not take place in any gasification plant on the surface, but it will be taking place underground. So, by that way we can remove the possibilities of emissions, etc. So, that is the philosophy of underground coal gasification. So, in this case air or oxygen and steam can be sent underground where coal is available, and this coal will be combusted and ash will form and the syngas will form. So, that syngas will goes up. So, it will come out as CO2, COH2, CH4 steam and tar. So, this is the concept, and people have studied on it mostly on simulation based studies, and some plants are also available for the underground coal gasification around the world. I will discuss that, but now I will see what are the advantage of this and what are the disadvantage. So, advantages over conventional processes are no reactor to be manufactured, low dust and noise, no ash handling at power stations, no coal stocking and transportations, larger coal resource exploitations, it converts sulfur to H2S and nitrogen to NH3 instead of SO2 and NOx. And it has some disadvantages, that is the potential for surface subsidence, possible aquifer contamination and expensive drilling and oil linking technologies. So, on the basis of the data the people have worked on it, it is evident now that coal seam is more than 2 meter thick. In that case this technology is feasible. It also requires seam depth more than 300 meter, and seam has more than 100 meter vertical separation from aquifers. These are the requirement for the UCG, and these are some example of the UCG based plants where the seam depth is provided, thickness of the seam is provided and quality of the coal is also provided. So, it is very clear that this method can be used for any type of coal, the quality of coal does not matter. So, that is the advantage of this technique, but we have some challenges in India, that is we lack of understanding of the technology, unavailability of proven track record and implementation guidelines, then regulatory framework governing UCG operations in the formulation stage, and then lack of understanding of the environmental impact of UCG and concern over the safety. So, these are the issues related with underground coal gasification. So, this is not a commercialized one, it is it has some issues also. So far we have discussed the possible options to produce cleaner energy from the coal. Thank you very much for your patience.